Assalamu alaikum. Welcome to this MATLAB tutorial. In this tutorial, I am going to teach you how to design the combined load frequency and voltage control model of thermal power system using transfer functions in MATLAB SIMULINK Software. I have taken an example from the book Power System Analysis by Hadi Sadat, Chapter 12, Example 12.9. Consider the example, which consists of an isolated power station having following parameters. As we are going to design the combined load frequency and voltage control model using transfer functions, therefore we need the time constant of various equipment used in the power system such as governor, turbine, inertia and load, speed regulation, amplifier, exciter, sensor and generator field in order to control both the frequency and voltage of the power system. The power system is working in normal mode when all of a sudden a load of 0.2 per unit is increased. Due to this, system frequency will vary. We have to build the Simulink model of the power system and measure this frequency deviation and terminal voltage in per unit as well as in actual values. Before going to model it in the Simulink, it is better to discuss here that when we are going to combine both load frequency and voltage control model, we have to derive few new equations in order to include the effects of both frequency and voltage on one another. Previously, in the automatic generation control topic, it was found that a small change in the real power is the product of the synchronizing power coefficient and the change in the power angle. If we include the small effect of voltage upon real power, we may obtain the following linearized equation. It may be noticed from the above equation that change in active power now includes the effect of both power angle and the voltage. Similarly, the small effect of rotor angle upon the generator terminal voltage may be included as below. Finally, modifying the generator field transfer function to include the effect of rotor angle, we may express the stator EMF as below. The above constants such as K2, K4, K5 and K6 depend upon the network parameters and the operating conditions. Including the above equations in the AGC system and the AVR system, a linearized model for the combined LFC and AVR system can be obtained. The mathematical solution as well as the basic model of this example can be found in the Hadi Sadat book. I am going to model it again in order to explain various other results which can be obtained from this model. For your convenience, I have uploaded the PDF link in the description section. You can download it from there. Let's start. Just click on the Simulink icon to open it. Click on this icon to open a new model. First, we need to save it. You may save it with any name of your choice and in any folder. To design the combined model of power system using the transfer functions, just look at its block diagram. It may be noticed that the model consists of transfer functions of governor, turbine, inertia and load, speed regulation, amplifier, exciter, sensor and generator field. It means that to design the combined model, we need the transfer function block, gain block, sum block and input signal step function block. At the first step, we need the add block and transfer function block for governor. To get the add block, go to Simulink library and take this add block from here and bring it in the model. Double click on this block. Put here two negative signs and press OK. Now we need the transfer function block. For this purpose, take the transfer function block from here and bring it in the model. Connect it with the add block and write here governor. The gain and time constant for governor are 1 and 0.2 as given in the example data. Therefore, double click on the transfer function block and write here 1, 0.2 and press OK. Look at the figure again. Now we need the transfer function for turbine block. For this purpose, just copy this transfer function block and paste it here. Connect it with the governor block and write here turbine. The gain and time constant for the turbine are 1 and 0.5 as given in the example data. Therefore, double click on the transfer function block, write here 1, 0.5 and press OK. Look at the figure again. Now we need the add block. For this purpose, just copy this add block and paste it here. Double click on it and put here one negative sign, one positive sign and one negative sign and press OK. Connect this block with the turbine block. Look at the figure again. Now we need the input signal which consists of change in load demand. For this purpose, we need the step input signal. Again, just look at the example data which shows that change in load delta P given in per unit is 0.2. To get this, go to sources and take the step input signal from here and bring it in the model. Connect it with the add block. Double click on it, a window will open. Write step time to 100. Put here 0.2 as initial value as well as final value and press OK. Look at the figure again. Now we need the transfer function of inertia and load. For this purpose, just copy this transfer function block and paste it here. Connect it with the add block and write here inertia and load. It may be noted that inertia constant h is 5 and d is 0.8 as given in the example data. Therefore, overall it becomes 1 upon 10 s plus 0.8. Double click on this block, write here 10, 0.8 and press OK. Look at the figure again. Now we have to put the speed regulation value. For this purpose, we need gain block. Take the gain block from here and bring it in the model. Connect this gain block with inertia and load block as well as with this add block to complete the feedback loop. Write here speed regulation. Speed regulation given in the example is 0.05 per unit. Therefore, 1 upon R will become 20. Double click on the gain block, put here 20 and press OK. Look at the figure again. Now we have to put this integrator block with this integral gain in order to bring back the system frequency to its original value after subjected to load variation. For this purpose, take the integrator block from here and bring it in the model. Connect it with here. Now copy this gain block and paste it here. Connect it with the integrator block as well as with this add block. Write here Ki to represent the integral gain. We may put any value for this gain because this value needs to be tuned again and again. However, in order to save the time, directly put 6 as this value and press OK. Look at the figure again. Now we need the add block as well as input signal for the reference voltage. For input signal, we again need step input function block. To get this, just copy this step function block and paste it here. Similarly, copy this add block and paste it here. Write here V reference to represent the reference voltage. Double click on the add block, put here one positive sign and one negative sign and press OK. As we know that the normal voltage for power system in per unit is always 1. Therefore, double click on this block, put here step time to 100, put here 1 as initial value as well as final value and press OK. Look at the figure again. Now we need PID controller to bring back the voltage to its original value. For this purpose, take the PID controller from here and bring it in the model. Connect it with the add block. Double click on the PID controller block and put here the values of P, I and D as 1, 0.25 and 0.3 respectively and press OK. Look at the figure again. Now we need the transfer function block for amplifier. For this purpose, just copy this transfer function block and paste it here. Connect it with the PID controller and write here amplifier. The gain and time constant for the amplifier are 10 and 0.1 as given in the example data. Therefore, double click on the transfer function block, write here 10, 0.1 and press OK. Look at the figure again. Now we need the transfer function block for exciter. For this purpose, just copy this transfer function block and paste it here. Connect it with amplifier and write here exciter. The gain and time constant for the exciter are 1 and 0.4 as given in the example data. Therefore, double click on the transfer function block, write here 1, 0.4 and press OK. It may be noted that by mistake exciter values are written wrongly. It is advised to correct it in your model in order to obtain the correct results. Now we need the add block again. For this purpose, just copy this add block and paste it here. Similarly, copy this transfer function block and paste it here. Connect it with this add block. Double click on it and put here one negative sign, one positive sign and press OK. The gain and time constant for the generator field are 0.8 and 1.4 as given in the example data. Therefore, double click on the transfer function block, write here 0.8, 1.4 and press OK. Write here generator field. Look at the figure again. Now we need the gain K6 block. For this purpose, just copy this gain block and paste it here. Connect it with the generator field block and write here K6. The value for K6 is 0.5 as given in the example data. Therefore, double click on this block and put here 0.5 and press OK. Now we need the add block again. For this purpose, just copy this block and paste it here. Double click on it. Put here two positive signs and press OK. Look at the figure again. Now we need the transfer function block for the sensor in the feedback loop. For this purpose, just copy this block and paste it here. Connect it with the add block here as well as with the add block here in order to complete the feedback loop. Write here sensor. The gain and time constant for the sensor are 1 and 0.05 as given in the example data. Therefore, double click on the transfer function block, write here 1, 0.05 and press OK. Look at the figure again. Now we have to combine both the models. It may be noted from the voltage equation that now we have to combine K5 with delta sigma plus K6 with E. However, it may be further noticed that before this we have to add integrator block here. Therefore, just copy this integrator block and paste it here. Similarly, copy the gain block and paste it here. Connect it with the integrator block and write here K5. Now connect it with the add block. The value for K5 is minus 0.1 as given in the example data. Therefore, double click on this block and put here minus 0.1 and press OK. Look at the figure again. It may be noted that change in electrical power is the sum of product of PS into delta sigma plus K2 into E. For this purpose, copy the gain block and paste it here. Write here PS to represent the synchronizing power coefficient. The value for PS is 1.5 as given in the example data. Therefore, double click on this block and put here 1.5 and press OK. Now copy this add block and paste it here. Double click on it and put here two positive signs. Now connect this add block with this block. Now copy this gain block and paste it here. Connect it with this add block as well as connect it here. Write here K2. The value for K2 is 0.2 as given in the example data. Therefore, double click on this block and put here 0.2 and press OK. Look at the figure again. It may be noted that generated voltage E consists of the product of generator field transfer function and the difference of the field voltage and product of K4 and delta sigma. It means we need again the gain block. For this purpose, copy this block and paste it here. Connect it here as well as connect it with this add block. Write here K4. The value for K4 is 1.4 as given in the example data. Therefore, double click on this block and put here 1.4 and press OK. Now at this stage our model is almost completed. Now we need the scopes to measure the frequency and terminal voltage. For this purpose, take the scope from here and bring it in the model. Connect it here and write here delta F in per unit. Similarly, copy this scope and paste it here. Connect it here and write here terminal voltage in per unit. Set the simulation time to 50 seconds. Now you can run the simulation. Double click on the scope to see the terminal voltage in per unit. It can be observed that due to PID controller, the terminal voltage has successfully recovered to 1.0 per unit for a load change of 0.2 per unit. Now double click on the frequency deviation scope to see the frequency deviation in per unit. It can be observed that due to integral controller, system frequency has restored to its original frequency. Therefore, the difference in the frequency becomes 0 as shown in the figure. To justify this, I am going to convert this frequency into original frequency as well as terminal voltage in volts. For this purpose, we know that the actual frequency is the sum of the base frequency and the change in frequency. Therefore, first copy this gain block, paste it here, connect it here and double click on it. Put here 60 and press OK. Now copy this add block and paste it here. Double click on this block, put here 2 positive signs and press OK. Connect this gain block with add block. Now take the constant block from here and bring it in the model. Connect it with the add block. Write here base frequency and here actual frequency. Double click on this block, write here 60 and press OK. Now copy the scope and connect it here. Write here frequency in hertz. Now you can run the simulation. Double click on the scope to see the actual frequency in hertz. It may be observed that frequency has successfully recovered to 60 Hz. Now I am going to measure the terminal voltage in volts rather than in per unit. We know that the actual voltage is the product of base voltage and per unit voltage. Therefore, copy this gain block and paste it here. Connect it here, double click on it and put here 11,000 and press OK. It is because normal generating voltage in the power system is 11 kV. However, if any particular voltage is given in the example, then we may put that particular value. Copy this scope and connect it here. Write here terminal voltage in volts. Now you can run the simulation again. Double click on the scope. It may be noted that due to PID controller, the terminal voltage has successfully recovered to 11 kV for a load change of 0.2 per unit. Friends, at this stage we have successfully designed the combined model of load frequency and voltage control of power system. Now I am going to highlight the new research trends in this topic so that any interested person may do his research. Number 1. Use the same model for 3 different load variation cases such as 0.05 per unit, 0.1 per unit, 0.15 per unit, and measure the frequency, voltage and power responses for all 3 cases. Number 2. You may also consider various intelligent controllers to compare their response with PID controller in terms of frequency, voltage, overshoot undershoot and settling time in order to show their effectiveness. Number 3. You can also design this combined model for two-area power system to introduce more complexity in the system. This will also be a good contribution. Friends, in the next tutorial, I will discuss how to tune the PID controller in order to get the desired frequency voltage response without overshoot and within minimum settling time. Friends, these are the few research topics that can be chosen by anyone to perform his or her research. That's all for today's lecture. I hope you really enjoyed this lecture. Friends, I upload many videos based on various topics of power system and motivation on regular basis. Therefore, don't forget to subscribe my channel in order not to miss my latest videos. And don't forget to share my videos with your friends and class fellows so that they can also get benefit from these videos. Thank you very much.